Have your homework, Ray. Laura. Fanny. Brandon. Lothar.
Yeah.
And I'll take your homework also either now or an email later. Okay. So we have been talking about cellular resolutions, right? And I hope that by now I have convinced you that having a cellular resolution is a very nice thing. It means that you can just look at these pictures and derive all this important algebraic information from them. And so what I want to do today, and probably also next class, is just to show you some examples of how you actually find cellular resolutions. Some examples of cellular resolutions. So, first of all, there's kind of a well, the first example is these staircase pictures that we were working with. In general, we saw that any monomial ideal in 3 variables can be resolved using a picture. Resolution of a monomial ideal in 3 variables by a planar map. And you just did this in your homework. So probably you guys did it differently. There were several ways of doing this homework, but one of the ways is, which is hopefully correct, is this one. So in the homework I gave you some monomial ideal in 3 variables, and then you guys found a picture that resolved it. And there were several possible answers, but you should have gotten something that looks kind of like this. So I think maybe, well, this is one of the possible pictures, right? And then, I don't know, these things were labeled like 2, 1, 1, 1, 2, 1, etc. So well, the thing is that actually, once you have a planar map like this, you can see it as a 3-dimensional polytope also. Just kind of rearrange things so that the outside border looks like a polygon, right? And then you can just imagine that you're staring at the big face of the polygon, and then of the polytope, a 3-dimensional polytope, and all this other stuff is off in the 3rd dimension. The point is basically that when you draw a picture like this, you can think of it as a polytope. And then you're going to get an example of a cellular resolution. Okay? And this shouldn't be a surprise, because we started with the goal of defining cellular resolutions using this as an example. We knew that we could do this in 3 variables, and we wanted to do it in more variables. Okay? So this is kind of the first example that started this whole discussion. So here's the second example. And it's something that we call the Taylor resolution. Okay. So it goes like this. Let's say that you have any monomial ideal let's say it looks like this. And then remember that what we want to do is come up with a polyhedral complex whose vertices are labeled by these monomials, right? Now, what's the simplest polyhedral complex that you can think of that has these things as labels on the vertices? Maybe it depends what you think is simple, but what I think is simplest is if you just choose a single simplex in R vertices. So that's going to be an R minus 1 dimensional simplex. And then you're going to put one of the monomials at each node. Okay? So that's what I'm going to do. Let X be the R minus 1 simplex. With vertices labeled by these guys. Vertex labels X to the AI. Okay. So I don't know. Let's do just a quick example of this. Maybe we have something like this: x to the 7th y cubed, x to the 8th y squared, x to the 4th y 4th, x cubed y to the 5th. Okay, so that's a monomial ideal in two variables. And so what I do is that I make a simplex of that number of vertices. In that case, I'm going to have 4 vertices, so I'm going to get a 3-dimensional simplex. Right? So X is going to look like this. It's just a simplex with labels like this: 7, 3, 8, 2, 4, 4. 3, 5, right? And then I'm going to get some resolution out of this. Now this is a full tetrahedron, okay? And then I get some resolution out of this. And this resolution is going to look like this. I guess we get first the one-dimensional faces. Sorry, the 3-dimensional phase, there's only one of them. Then we're going to get the 2-dimensional faces, and there's 4 of them. Then we're going to get the edges, so there's 6 of them. Then we get the vertices, and there's 4 of them. Sorry, these shouldn't be F's, these should be R's, right? Copies of our ring. For vertices, and then depending on whether I want to resolve I or R mod I can either put I here, or I can put another R and then R mod I. But I get this free resolution in this case. Okay? And we know how to get the shifts, right? For example, these are the vertices, and so the shifts that we get are the labels of the vertices: 7, 3, 4, 4, 8, 2, 3, 5, and then we put here the labels on the edges, and remember that those are determined, right? So for example, this edge between 7, 3 and 4, 4 gets labeled the LCM of these two things, which is x to the 7th, y to the 4th. So we get a 7, 4 here, and so that's going to be one of the shifts here, etc. Okay? And we know how to do this very explicitly. So I claim that this actually is a free resolution of I. This is really a cellular resolution. So do you remember what I need to check to make sure that that claim is true? Yes? What do I need to do? So I need to look at this, and I need to make sure that it's acyclic for any b. Right? That's the condition that needs to hold so that this is really a cellular resolution. Okay? So I claim that this is true in this case. Why is that? Well, because, I don't know. Let's do, for example, x less than or equal to 7, 5 for this example. Okay? I think this example will show you how the rest goes. So maybe the first thing that we can ask ourselves is what vertices of x get to live in here. And it's just whatever vertices are less than or equal to 7, 5 coordinate-wise, right? So in that case, we get 7, 3. We get 4, 4. And we get 3, 5. Sorry, I'm talking about the vertices so far, so I don't get to put these edges yet. Okay? So these 3 vertices live in this subcomplex, but this other one doesn't. Okay? Now, what I claim is that if these 3 vertices live in this subcomplex, then the whole triangle has to live in there. Why is that? Well, because if 7, 3 is less than or equal to 7, 5, and 4, 4 is less than or equal to 7, 5, then when I take the coordinate-wise maximum, I still can't beat that 7, 5. So that means that this guy is also in there, this guy is also in there, this guy is also in there, and the whole face is also in there. Right? Because all of the vertices have first coordinate less than or equal to 7, second coordinate less than or equal to 5. So once I have these 3 vertices, the whole triangle is in there. But I also claim that nothing else gets to be in there. And why is that? Because every other edge, or every other triangle, or every other vertex, one of its vertices is excluded, and that means that the face has to be excluded, right? If the vertex 8, 2 doesn't live here, then I also can't have any edge that contains it. Okay? So what we see here is that this guy is just a simplex. Is the simplex whose vertices are labeled with monomials less than or equal to b. And because it's a simplex, that means it's a full simplex, so there's no holes there, there's no homology. Okay? So that's it. That's a proof. Okay. Any questions? So this thing, f sub x, is called the Taylor resolution of I. Okay. So what does this say? This says that actually for any ideal, I mean, I didn't put a single condition on this ideal. I just said it could be any monomial ideal. For any ideal, I can make this construction. For any ideal, there is this very simple picture of a simplex, and that simplex is always going to resolve my ideal. In other words, finding some cellular resolution actually is very easy. This is just a very straightforward construction that always works. Okay? So that's good news, because that means if you have nothing else, at least you have this. Okay? Now, what's the disadvantage of this thing? The disadvantage is that, for example, what is the length of this free resolution that we wrote here? It took us, we started with the ideal, and it took us 0, 1, 2, 3 steps to resolve it. 3 plus the 0, so really 4 steps. Okay? And that comes from the fact that this thing is three-dimensional. Okay? We have 4 steps corresponding to the fact that that's the dimension plus 1. It's the number of vertices. In general, if I had R generators here, then this would be an R minus 1 dimensional simplex, and this would take me R steps. Okay? So the Taylor resolution has length R. Okay? Now, does that seem short or does that seem long to you? I see some of you kind of muttering long. For example, for this ideal, how many steps would you expect to take? Just 2, right? Because there's 2 variables. So we know by the Hilbert-Syzygy theorem that if you have n variables, it's only going to take you, it should only take you n steps. So here it took us 4 steps, but we know that we can resolve this same ideal in only 2 steps. Okay? Now, in general, I don't know, let's say that this lives in variables. Okay? But we know that I can be resolved with length less than or equal to n. Okay? And so you can imagine that, I don't know, if I give you an ideal in, I don't know, let's say 10 variables with 100 generators, then this would be a resolution of length 100, when actually you know that there is a resolution of length 10. Okay? And so that means that this is some resolution, but it's going to be one that's difficult to work with, probably, because it's very big. So generally, this is too big. Okay. Ideally, what we want is the minimal free resolution. Okay. And in this case, almost certainly, we're not going to have the minimal free resolution, because it looks like, I mean, unless you have very few generators, you have no hope of being minimal here. Okay. So the good news is that it's an easy resolution. The bad news is that it's too big. Okay? So that's kind of the simplest example. Now, for the next example, what I want to do is I want to show you an example of a cellular resolution for a very concrete ideal. Okay? And this is something called a permutation ideal. Already from the name, you can tell that this is going to be a pretty combinatorial thing. So for example, let's, so we start with some vector in Rn. I actually want n to the n. Okay, so I want an n tuple of natural numbers. Then the permutation ideal corresponding to this is an ideal that we denote I of u, and by definition, this is the ideal generated by the following things. So it's an ideal in n variables, okay? And so what you're going to do is, one of the generators is just x to the u. Okay? So I don't know, if u was 1, 3, 2, then one of the generators is x, y cubed, z squared. But the reason we call this a permutation ideal is that now you're going to just move your variables around in every possible way. So I'm going to permute u in every possible way. Okay. So here Sn denotes the symmetric group, the group of permutations. And so that's what I do. And again, I think this is clearest in an example. So the ideal of 1, 2, and 3 will be something in 3 variables, and it's going to look like x, y squared, z cubed, x, y cubed, z squared, x squared, y, z cubed, x squared, y cubed, z, x cubed, y, z squared, and x cubed, y squared, z. Because there are 6 permutations of the numbers from 1 to 3. Okay. So this lives in variables, yeah? So let me ask you a question. How bad is the Taylor resolution here? Pretty bad, huh? It's pretty bad because we have n factorial generators, and so the Taylor resolution is going to take n factorial steps. But we only have n variables, and so really we expect to take only n steps. So that's how you can see how dramatically bad Taylor resolutions can be. You know, where instead of taking n steps, you take n factorial steps, right? Instead of 4 steps, you take 24. Instead of 5 steps, you take 120. So what we want is a more efficient way of encoding this. We want a more efficient picture that doesn't take up so many dimensions, and so that's what we're going to do. Okay? So what do we need to do? We need to come up with a polyhedral complex whose vertices are labeled by the permutations. Okay? Does anybody know such a thing? Permutahedron. There's something called a permutahedron. Have you heard of it? Some of you have heard of the permutahedron, some of you haven't. So what's the permutahedron? It's precisely a polytope whose vertices are the permutations of U. It's called the permutahedron. So actually, all of you have seen a permutahedron before. So I found out last year. I'll tell you why in a second. But the permutahedron P of U is the following thing. It's the convex hull of all the permutations of U. Okay, so it's a polytope whose vertices are given by the different permutations of U. So for example, the permutahedron 1, 2, 3 has 6 vertices. And let me be lazy and not put commas everywhere. So for example, one vertex is 1, 2, 3. And by that I mean the vector 1, 2, 3 in 3 dimensions. 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, 3, 2, 1. Okay. And well, this lives in R3, right? And this thing lives in Rn. Okay, so let's try to draw this guy. Well, as you can probably guess, I already did over there. Except I'm realizing that I did it wrong. So I have to fix it, but it's mostly okay. So this is the permutahedron. The black thing is the permutahedron P of 1, 2, 3. Okay. So you might be a little bit confused about the fact that I told you that this was going to be a 3-dimensional thing, but I'm saying that this permutahedron is a hexagon. Okay. But the thing is that if you really go and plot these 6 points in 3-dimensional space, which I did here almost correctly, but let me do it correctly now. Actually, it'd be a good exercise for you to think about why I had it wrong. I mean, yeah, of course, that's the first question, right? And that I can't possibly get right. But the well, I haven't told you what axis is what. So there's only one thing that I need to get right, which is whether I should put 1, 3, 2 here or here. And that's what I might have right or I might have wrong. I think I have it. I think it's like this. It's a good exercise for you to think about why this is. But so you always go to the neighbor vertex by swapping 2 adjacent things. So here we swap 3 and 1, we get 3, 1, 2. We swap the 1 and the 2 and we get 3, 2, 1. We swap the 3 and the 2. Did I do something wrong? I'm not convinced that I'm doing this correctly. So you should do this correctly. And what I'm going to do, actually, I know that I'm doing it incorrectly. So really, in some order, these vertices look like this. But we can do it. Just help me and we can do it. So let's start by labeling the axes, okay? So that's the start. Now, you see Z is going up. So that means, and this is why I knew I had it wrong. These guys should have Z coordinate 1, Z coordinate 2, and Z coordinate 3. Now, these guys, according to the X coordinate, well, let's do Y first. So according to the Y coordinate, this should be 1. 2, this should be 3. And according to the X coordinate, this should be 1, and 2, and 3. That's right. And the way that you get from a vertex to a neighboring vertex is by switching not to adjacent positions, but to adjacent numbers. And if you took my Coxeter groups class, you know what a headache it is to remember whether it's positions or numbers that you're supposed to switch. And that's why, but now it's right. Okay, so this is really the permutahedron 1, 2, 3. Okay? So what I would like to say is that this is a much better way of resolving my permutation ideal than the Taylor resolution. Now, of course, the point is that the permutahedron looks, I mean, it already comes with a labeling of the vertices, right? And that's the labeling we're going to use. Okay. And so then, using those vertex labels, I'm going to give labels to the edges and to the full thing. Okay. So the other thing that I meant to tell you is that I know you have seen the three-dimensional permutahedron if you have been to a playground in the last 5 years. So there's this thing that looks kind of like a sphere, but it has hexagons and squares. That's the three-dimensional permutahedron. So clearly there's some mathematician behind that design. But okay. So what I want to do is basically use the permutahedron to resolve the permutation ideal. Okay? So that's our goal. Goal is to show that when we do the free resolution with respect to this permutahedron, we will show that this is a cellular resolution of our ideal. Okay. Now, how long is this resolution? Well, cellular resolutions go by dimension, right? You put the full dimensional things, then the next dimension, and the next dimension until vertices, etc. Okay? So if we want to know how long this cellular resolution is, we just need to say how many dimensions this thing lives in. Okay? And well, at most it's n dimensions because this thing lives in n-dimensional space. But actually, I'm going to show to you that it's always the case that you lose a dimension, just like you do here. This picture looks like it lives in, it lives in 3 dimensions, but it's 2-dimensional. And the permutahedron lives in n dimensions, but it's n-1 dimensional. And so that means that we can do this in n-1 steps. Okay. And that's a lot better from n factorial to n-1. Okay. And that's a lot better if you're a combinatorialist, because that means that you are translating the algebra of the permutation ideal to the combinatorics of the polytope. This is the guy you want to understand. And so that's what we should do. Okay? So let's talk about the permutahedron for, I think, the rest of the hour. Okay? So for example, can you see why this thing lives on a plane? Okay. In other words, can you tell me what the plane is? The equation of that plane? The sum of the coordinates is 6, right? Because it's a 1, a 2, and a 3. And you see in general, that's also true, that no matter how you permute these numbers, they're going to have a constant sum. Okay? So here's the first fact. This permutahedron lives on the hyperplane given by coordinates x1 plus, etc., plus xn equals a constant. And what's that constant? It's u1 plus, etc., plus un. Okay. So it's at most n-1 dimension. And it turns out that it is exactly n-1 dimension. And that's why I need n-1 steps. Okay. Let's talk about the faces of this thing. So, the thing is that eventually, I want to say what I just said, right? That the resolution of the permutation ideal is encoded in the faces of the permutahedron. So I need to understand what the faces of the permutahedron are. So the faces of the permutahedron are in one-to-one correspondence with the order partitions of numbers from 1 up to n. And what is this? It's the ways of writing n as a union of some sets that are pairwise disjoint. Okay. So, how am I going to prove this? Well, maybe before I prove it, let's see what it says over here. So let me just call these guys like this. And I'll just separate them by dashes. And the only reason that I want to do that is because I want them to look like partitions of the set, ordered partitions. So for example, when I write 2, 1, 3, I want you to think that I'm partitioning the set from 1 to 3 into 3 sets. The first set is 2, the second set is 1, the third set is 3. Okay. And so for each vertex, I get one of these partitions into n pieces. Okay. Now, if I force you to give a name to this edge right here, what name would you give it? Well, somehow I want to summarize that it contains these two vertices. And the name needs to be a partition. So I think that the most natural name to give it is 1, 2, dash 3. So let's call it that, 1, 2, dash 3. What about this guy? Well, that should be 1, dash 2, 3. This one is what? Is it 3-1, 2 or 1, 2-3? This didn't quite work out the way we wanted it to. So what I'm gonna do is something different. What I'm gonna do is the following. I'm gonna actually tell you where are the, okay, what is it that I want to do? I want to tell you where are the 1 and 2, and where is the 3. So I think I just started it out wrong. What I want to do is the following. Again, it's the same issue of positions. Do I record positions or do I record numbers? So we were recording numbers, but actually what we want to record is positions. So let's start over. Okay. And it's going to work out this time. So what I want to do is I want to look at my picture over there, and I want to record first, where is, for example, the thing is that, let me just write down the black names here. Okay, so I think this is what I should do. Instead of just reading the permutation, what I'm going to do is say, where is the number 1? Then where is the number 2? Then where is the number 3? Okay. So where is the number 1? It's in the second position. Where's the number 2? In the first position. Where's the number 3? In the third position. Okay. Here, where's the number 1 in the second position? Then 2 is in the third position. And then 3 is in the first position. Is it clear what I'm doing there? So I'll do the rest, and in the meantime, please make sure that it's clear. It's important that it's clear. So 1 is in the third position, 2 is in the second, 1 is in the first. 1 is in the third position, 2 is in the first, 3 is in the second. 1 is in the first position, 2 is in the third, 3 is in the second, and 1 dash 2 dash 3. Okay. And these are going to be the labels of the vertices. Okay. If you think about it, what I'm writing here is just the inverse permutation of the one that I have on the vertex. Okay. And now I think that the plan that you had for how to label everything is going to work. Okay. Because now you see, I want something between this and this. And now that gets to be 1, 2, dash 3. Then this gets to be 1, dash 2, 3. Here, what should I label this thing? 1, 3, dash 2. See, now it works nicely. This should be 3, dash 1, 2. This should be 2, 3, dash 1. And this should be 2, dash 1, 3. And then I should also label the inside thing, which is 1, 2. And now I'm going to erase my black vertices, so my black names, so I don't get confused. Okay. So this is how I do it in this example. And if you look at this, these are all the possible ways of splitting up the set 1, 2, 3 into pieces in order. Okay. So I want to prove that it's always like this. So let's do that. So proof. Well, we can start over here. Let me just take a phase of P of U. Okay? So a phase of P of, and let's just for concreteness do a specific U, but you'll see that this generalizes for anything. So let's say, for example, that this is our U. Okay? It's of length 6. So that means that we're looking at the 6th permutahedron, which lives in 6 dimensions and has 6 factorial vertices. I guess that's like 720, something like that. So how do I specify a phase of this thing? Well, remember that now a phase means something very precise to us, right? It's no longer that thing that we look at over here. What a phase is what's given by a linear function. You choose any linear function, you see what vertices maximize that linear function, and those are going to determine your phase. So a phase of this thing is determined by the vertices maximizing some linear function. Okay, So let's say that our linear function is something in 6 variables because we live in 6 dimensions. And I'm just going to choose something like this maybe. Okay. So what am I asking here? I'm asking for the vertices that maximize this. But a vertex is just a permutation, right? So which permutations of 1, 2, 4, 5, 7, 8 maximize this? So you see, this is a very concrete kind of optimization question. I give you a linear function, and I'm asking you to put in a permutation of the numbers 1, 2, 4, 5, 7, 8 into this function so that you get the largest possible result. What should I do? Well, basically what I'm saying is x1 gets a lot of weight, so I should put a big number there. Right? And I mean, these 3 guys are the ones that carry the most weight, and so I should put my 3 largest numbers there. So I should put at x1, x3, and x6, I should put my numbers 5, 7, and 8. Once I've done that, then I go to the next most valuable ones. Okay. And what numbers should I put there? Well, I already wasted I didn't waste them. It was very nice that I put the largest numbers here, and then the next smart thing that I can do is put the next 2 largest numbers here. Okay. And then finally, in the last position, which really is like having a 0x4, right? I didn't write it, but it's just something that has weight 0. There I should put my smallest number. Okay. Now, what was I saying in my labeling of my permutahedron? I was saying, let's first say where the 1 goes, then where the 2 goes, then where the 3 goes, etc. In other words, I was just going from smaller numbers to bigger numbers and telling you what position they were in. Okay? So when I do that over here, this corresponds to the ordered partition where the smallest number goes in position 4, then the next 2 biggest numbers go in positions 2 and 5, and then the next 3 biggest numbers go in position 1, 3, 6. So what I'm saying is that given any linear function, there is a clear natural way of assigning an ordered partition to it. This is it. And this basically tells you the correspondence, and then the other thing you have to check is that given an ordered partition, you have to find the linear function. But you see that's not very hard, because if you want to get this ordered partition in the end, then what you do is just reverse this, right? You just give 4 the lowest weight, you give 2 and 5 the medium weight, and you give 1, 3, and 6 the highest weight. Okay. So that's how that goes. Okay. By the way, we should also say what is the label of that face? I think I don't need the, let's see. No, I'm not going to need this anymore. Maybe we'll keep the permutahedron, but not the other stuff. So what is this face? The vertices on this face. Well, let's call this face F. So what are the vertices on F? How many vertices are there? Well, the first number has to be 4, right? Then the second and third position has to be either 2 or 5. And then the third position, then the last positions. These two have to be 2 and 5. So either it's 2, 5 or 5, 2. Okay. And then 1, 3, 6. Well, that goes in every possible order. So you can have either 1 or 3 or 6. I mean, you see what I'm doing here? Basically, I'm saying that the vertices have to be those things where the first coordinate is a 4, then the second coordinates are 2, the second and third coordinates are a 2 and a 5, and the last coordinates are a 1, 3, and a 6. So one of the vertices is 4, 5, 2, 6, 1, 3. How many vertices are there? Well, I have 2 choices for how to organize these guys, and I have 6 choices for how to organize these guys, so there's 12 vertices. Okay. Now, each one of these things comes with a label, right? For example, 4, 5, 2, 3, 1, 6 gets labeled x1 to the 4th, x2 to the 5, x3 squared, etc. Okay. So what's the label that F gets? Well, it's the least common multiple of all of those labels. So what do I get when I take the least common multiple of all the permutations of this form? Well, in the first position, everybody has a 4, so I get a 4. In the second position, we either have a 2 or a 5. We're taking the least common multiple, so that's going to give me a 5. In the third position, I'm also going to get a 5. In the fourth position, in the fourth position, I made a mistake. Again, I changed labels and vertices. What I want is that in the fourth position, I have to have a 1. Right? In the second and fourth positions, no. In the second and fifth positions, I have to have the 2 and the 4. And in these positions, the first, third, and sixth positions, I have to have the 5, the 7, and the 8.